Meta just built a storage system that can hold 50,000 terabytes. That's 50 petabytes of data in a single storage rack. Now, if you think of it, that can hold about 10 million 4K movies in one go. And it's all built on flash storage that most people thought was just too slow to ever be useful. Hey, my name is Vikram Shekhar and welcome to the channel. I write a Substack publication called Vik's Newsletter where I write a whole lot of stuff about semiconductors. And on this YouTube channel, I'm going to talk through a lot of the articles that I write. So if you ever need to have greater depth and more detail, check out the link in the description below. The fundamental flash memory cell is essentially a transistor that has an extra gate or charge storage layer that can hold and release charges on demand. Now, the older form of flash memory was built with an extra floating gate that could hold electrons. But later implementations of the flash storage cell used a charge trap layer built out of silicon nitride that could hold or release electrons when asked to do so. Most modern flash technology today uses the charge trap technology. But for the sake of generalization, we can refer to this layer as a charge storage layer. So let's understand how this transistor works. When there is no voltage applied at the control gate, there are no charges stored in the charge layer. And the threshold voltage of the transistor is pretty low, which means that by default, current is flowing at the readout voltage. When current flows at the readout voltage, it essentially represents a bit state of 1. When a voltage is applied at the control gate, the charges are pulled from the P substrate into the charge storage layer. And these are predominantly electrons. And so when electrons are present in the charge storage layer, the threshold voltage of the transistor moves to a higher value. And so at the gate readout voltage, now there is very little current flowing, and this represents a bit state of 0. This is called a single layer flash cell, or SLC. To erase the cell, a voltage is applied to the P substrate and the electrons are pulled out of the charge storage layer, and the threshold voltage of the transistor goes back to its low value, resetting it to a value of 1. Now, this very mechanism of turning on and off the transistor and storing a charge of 0 or 1 involves electrons tunneling through an oxide layer. If you do this enough number of times, the oxide layer eventually degrades and the cell breaks down. So this is why flash memory has endurance problems, especially when you write to it. So with a single layer flash cell, you can store either a 0 or a 1. But there is no fundamental reason why the number of bits stored has to be 1 bit to a cell. Because if you can put more electrons into the charge storage layer, you can increase the threshold voltage even more. And this is the fundamental idea of a multi-level cell. In a multi-level cell, or MLC, you can have 4 different charge levels stored in the charge storage layer, which corresponds to 4 different threshold voltages of the transistor. So to quickly recap, a single layer cell has 2 different states and can hold 1 bit of information, and a multi-level cell, or MLC, can hold 4 different levels, and that corresponds to 2 bits to a cell. Now, the idea can be further extended to holding even 3 bits to a cell, which would result in 9 different states of the cell. And this is called triple level cells. And finally, we come to what is the modern implementation, or the state of the art in flash memory is actually quad level cells, where you store 4 bits or 16 different reference levels to a single memory cell. And researchers are taking this to add yet another bit to create a penta-level cell, or PLC. You get the idea. So now that we understand all the levels of cells from single layer cells all the way to penta-level cells, what is the trade-off when you keep adding different number of bits and storing more charge levels in a transistor? One of the biggest problems is latency. When writing to a cell, what is often used is called an incremental step pulse programming method to apply voltage to a cell. So this means that you don't apply the entire voltage all at once. Instead, You apply a gradually increasing voltage in steps, which means you apply a given voltage and then you verify if the voltage is the right value. If it hasn't reached that yet, you apply another pulse and then you verify again if the voltage has reached the correct value. If you have many different voltage levels, like in the case of a quad level cell, then you need to have a very precise number of steps and a lot of steps and a lot of verifications to make sure you're writing in the correct voltage to reach the correct charge density that is stored inside the cell. As a result, the more voltage references you add, the longer it takes to write to the cell, thus increasing its latency. Now, the endurance also gets worse as you add bits to it. And the reason for that is that as the tunneling happens across the oxide, when you program the cell to different levels, which means you're taking charge in and out of the charge storage layer through tunneling through the gate oxide, it doesn't break down all of a sudden. So what actually happens is that it gradually starts to affect the transistor's performance, which means that a transistor starts to have threshold voltage shifts when it should not have any of them. And especially when you have 16 different voltage levels where you have to distinguish between, it becomes very difficult to tell which voltage is being stored in the cell if the threshold voltage is also continuously changing. Thus, endurance gets pretty bad as you add more bits or voltage levels to a single cell. The other problem is that it has worse thermal stability because the process of tunneling and the environment that the flash drive is located in heats up. And when the flash cells heat up, their threshold voltage also shifts. And now it becomes even more difficult to distinguish between the different voltage levels that are stored in the cell. And therefore, adding more bits to a cell makes it very sensitive to thermal performance. The only major advantage of adding more bits to a single flash cell is that you can increase its capacity and memory density by orders of magnitude by just making each transistor cell hold more levels of charge. And QLC based SSDs are basically becoming hot commodity in AI data centers today because we need to store so much data. And so there are storage manufacturers like Micron, Kioxia, Samsung, SanDisk, who all have their own versions of QLC drives with PCIe Gen 5 or Gen 6 interfaces that can provide both speed and capacity for AI workloads. If you want to dig deeper into this subject, I'll leave the link to the whole Substack article below, where I discuss the use of QLC SSDs in AI workloads, how they fit in the storage hierarchy between TLC-based SSDs and hard disk drives, what kind of CPU performance is required, what are the major bottlenecks of using QLC-based SSDs, and a general rundown of all the market players today. Thanks for watching and subscribe if you haven't to the channel already. I'll catch you on the next one.